Oh, great. You came back. Well, thanks for coming. In part two of this video series, we begin by establishing definitions for temperature, heat, and thermal energy, and then I'll show you an example of how they all relate to each other. So, what exactly is temperature? If you're like most normal people, you talk about temperature as a way of describing whether something is hot or cold, or maybe just warm. But I think you'll agree that these are subjective, qualitative terms. When my grandma told me to turn the thermostat up because it was too cold, I could never understand why she wanted it to be 80 degrees in the house. So you see, it's a very subjective measure. To really understand temperature, we must ascend to the atomic level of matter. And to do this, I'd like to introduce you to one of the computer simulations developed by the University of Colorado Boulder's Physics and Engineering departments. So let me see if I can switch over to this. Okay. Alright, let me clean things up a little bit here. Okay, so here we have a computer simulation, and let's pump the handle and get some atoms going. So here you can see the particles of a gas, helium let's say, moving around in a container at approximately room temperature. Here's a thermometer here so you can monitor the temperature. At first, I'd like you to fix your gaze on the atoms for a few seconds and notice that at any given snapshot in time, some atoms are moving quite slowly while others are moving rapidly. Most atoms are moving at intermediate speeds. Interestingly, if you look carefully, you'll see that these slow atoms don't stay slow for very long. Almost before you can blink an eye, they get whacked by another atom and then start moving much faster. The simulation provides a neat analytical tool that allows you to plot the distribution of speeds and kinetic energies on a histogram. Let's see if we can pull that up. Okay, so let me pull this over so that you can see what's going on here. Okay. This shows us graphically what we're seeing visually in the chamber. A few atoms move very slowly and a few are moving very rapidly. You can see here on the speed distribution plot, there are atoms that are moving quite slowly down at this end, and then at the high end of the speed scale, every once in a while you see some atoms that are moving very fast. There's also a kinetic energy histogram up here at the top, and you can see, kinetic energy relates to the speed of the atoms. As the speed of the atom gets higher, the kinetic energy gets higher as well. What I'd like you to notice most of all is the overall shape of the distribution at a temperature of 300 Kelvin. See, the temperature is approximately 300 Kelvin. Let's see if I can bump it up a little bit. Oops, overshot just a little bit, but I'll see if I can get it right around 300. Okay, close enough, 301. Now, just take a look at the histogram, the overall distribution of speeds, just to kind of get a feel for how fast the atoms are moving at this temperature. Okay, and now let's add some heat to the collection of atoms and see if we can detect a difference in their motions. So I'm going to raise the temperature. I'm going to basically double it to 600 Kelvin. And I'm again trying to, there we go. Okay, so now we have the temperature twice what it was before. We've gone from 300 Kelvin to 600 Kelvin. I know that I've not introduced you to the Kelvin scale yet, but that's coming up in just a few minutes. But just suffice it to say that this is a temperature scale that we can use. Okay, trying to get it back up to 600 there. Okay, now at a temperature of 600 Kelvin, you should be able to see visually, with the motions of the atoms, that most of the atoms are moving significantly faster than they were at 300 Kelvin. So let's see if the speed and kinetic energy distributions reflect that change. So if we come over here, and I think you can see that indeed the distributions of speeds and kinetic energies have shifted to the right or to higher speeds and higher kinetic energies. So now I'm going to minimize this, and let's go back to our PowerPoint presentation. So this then brings us to a more scientific definition of temperature, which is the temperature is a measure of the average kinetic energy of the particles in a material. So as the temperature goes up, the average kinetic energy goes up. And the same is true if you know the kinetic energy is going up, or if the kinetic energy is going down, the temperature is going to correlate with that as well. Looking once more, let's look once more at this sample of helium atoms. And what I would like to emphasize now is if you could, theoretically, if you added up all of the kinetic energies of every atom in the sample at a given instant in time, you would determine what we call the total thermal energy of the sample. And so now here is our working definition of thermal energy. Thermal energy is the kinetic energy associated with the random motions of the atoms and molecules in a sample. Next, now let's look at two different temperature scales, Celsius and Kelvin. The Celsius scale was invented in the early 1700s by Anders Celsius from Sweden. He's a fine-looking lad. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. While theoretically there's no upper limit to temperature, there is a lower limit. This lower limit is called absolute zero. On the Celsius scale, absolute zero falls 273 degrees below zero. If you think back to how we just defined temperature, can you guess what would happen to the motion of the atoms of the gas if it were cooled to absolute zero? If you're thinking that they would stop moving completely, you're right. As it turns out, the physics of low temperature tells us that it's impossible to reach absolute zero. However, this has not stopped scientists from trying. Several labs around the world have achieved temperatures within 1/billionth of a degree above absolute zero, which is colder than any place we know of in the universe. In the mid-1800s, William Thomson, later known as Lord Kelvin, there he is, Lord Kelvin proposed a temperature scale similar to the Celsius scale, but with the zero set at absolute zero. This scale came to be known as the Kelvin temperature scale in his honor. Because the Kelvin scale starts at absolute zero, there are no negative temperatures on this scale. Converting between the Celsius and Kelvin scales is easy. Kelvin is simply equal to 273 plus whatever the temperature is in Kelvin. We're now in a position to define heat. Heat is closely associated with the zeroth law of thermodynamics, which says that when two objects come into direct physical contact with each other, heat will flow from the hotter to the colder object. It's also interesting to think about this law in reverse. If no heat flows between objects when they're placed in contact, then what must be true? That's right, they must be at the same temperature. Here's a simple illustration of heat. So let's say we have two objects that are in physical contact with each other, and the object on the left, the one in red, is at a higher temperature, T1, than the object on the right, which is at T2. Since they're at different temperatures, by the zeroth law of thermodynamics, we know that heat will flow between the two from the hotter object to the cooler object. And that heat will flow until the temperatures become equal. And at that point, we've reached what's called thermal equilibrium. Thermal equilibrium is the point at which the temperatures of the two objects in contact are equal to each other. So this allows us to arrive at our working definition of heat, which is the following. Heat is the transfer of thermal energy between two objects due to a temperature difference. And it's as simple as that. So again, the only time you're going to have heat is when there is a transfer of thermal energy because two objects are at different temperatures. Finally, let's take a look at a simple scenario that will hopefully bring all three of these concepts together for you. So consider these two samples of a gas. In the container on the left, sample A, the atoms are moving faster than the atoms in sample B. And you can see that there are 4 atoms in the A sample, whereas there's 16 atoms in the sample B. Let's just say that we've carefully added up the total kinetic energies of these 4 particles, and let's say that that energy happens to be 20 joules. And if we do the same thing for these 16 atoms, the total thermal energy is 32 joules. Okay? So these two energies represent the thermal energy contained in each sample. Now, here's a question. Based on what you can see here in this scenario, which sample is hotter? That is, which one has a higher temperature? Hopefully you picked A. Sample A has the higher temperature. Because these atoms are moving faster than the atoms on the right, the temperature must be hotter. Remember, because the definition of temperature is it's a measure of the average kinetic energy. So since the kinetic energy on average is higher for these guys, the temperature has to be higher. And so let's represent the temperatures sort of schematically by these two thermometers. Now, if we were to connect these two samples with some sort of a physical connection where thermal energy could flow, in what direction would the heat flow? So hopefully you remember from the 0th order of thermodynamics, heat must flow from the hotter to the cooler object, and so heat's going to flow from left to right. Now, as the thermal energy is being transferred, watch what's happening to the speeds of the particles in both containers. So I'll kind of toggle back and forth between frame 1 and frame 2 a couple of times. Do you see how the atoms in sample A are getting a little bit slower and the atoms in sample B are getting a little bit faster? And this is exactly what you'd expect, since the atoms in sample B are gaining thermal energy. And finally, once the temperatures are equal, then the transfer of thermal energy stops, heat flow stops, and we come to thermal equilibrium. How much heat was transferred? Well, if we go back to the initial slide, you can see that sample A started with 20 joules of thermal energy, whereas sample B had 32 joules. So let's just remember this number here, 20 joules for sample A. At the end of the heat transfer, we're down to 10 joules. So we went from 20 joules to 10 joules on the left side, and over here sample B went from 32 joules up to 42. So consequently, you can see that 10 joules of thermal energy was transferred, and the temperatures became equal. Okay, so just to summarize, we established the working definition of temperature. We saw that temperature is proportional to the average kinetic energy of the particles in a sample. The SI unit for temperature is the Kelvin, which is represented by the symbol K. But we also use the Celsius temperature scale for a lot of lab work. We define thermal energy, we define Q, which is the transfer of thermal energy between two objects due to a temperature difference. We defined what we mean by thermal energy, and we also read and learned about the zeroth law of thermodynamics, and we saw how that relates to heat and temperature. Okay, so that's it. Thanks very much.